He Oh, thank you, Emma. He graduated summa cum laude in physics at Princeton. And then he went to UC San Diego for graduate school, worked on gas dynamics of distant galaxies with Arthur Wolf. He was then a Carnegie and Hubble Fellow at Carnegie Observatories, and then moved to UC Santa Cruz about the same time I did. And I think about the same time you were doing a postdoc there, in 2002. And I met him on a softball team, physics softball team, where he was mediocre softball player.
That's also fair.
And he's now a distinguished professor of astronomy and astrophysics at UC Santa Cruz, but he recently made a switch into oceanography. He had been dabbling, I think, for quite some time, and now officially he's a pivot fellow at the Simons Foundation. So he's on professional development leave right now from Santa Cruz for a year. And he's here to talk to us not about oceanography, but about fast radio bursts.
Thanks, Brian. Thanks for having me.
And I'm going to leave now and leave you capable hands of Deborah. So I'll watch from the office.
And yeah, my first time in any of these buildings. Didn't even know this park existed. Well, maybe I did. I'd never visited it, so thanks for having me. It's great to be here. And yeah, fast radio burst will be the talk today. I was told to go 50 minutes and no more, so I won't. I didn't realize I was going to say congratulations to, I can't forward my slides, I can, to 2 directors today, but I have. So if you hadn't heard, Keck has a new director as of this morning, Rich Masuda, no longer interim, they took the title away, but he remains director. And congratulations to Director Lotz, who's perhaps attending her last seminar here. Fast radio bursts. I'm here on behalf of a team that's a pretty small size, about 15 persons. You'll see most of them in the next 2 slides. Several of whom were related to Art Wolf directly. I guess maybe 2 of whom, myself and Regina Jorgensen. There's gonna be some telescope quizzing today, so get your mindset there. I would have failed naming most of the Nora Lab telescopes, so but nevertheless, we'll do some telescope naming. MMO, what's MMO stand for? One of the observatories of the United States. Multi-mirror? No, it is not the multi-mirror observatory. Is that even an observatory? The Mariah Mitchell Observatory. And who is Mariah Mitchell?
I know, because I was a Mariah Mitchell fan.
Oh no!
That was a long time ago.
Do you want? That's fine. Do you want to tell us where the observatory is located?
It's on Nantucket,
True.
Nantucket Island.
Where I was honeymooned with my wife 29 years ago.
Which is like the best summer internship program ever. And Mariah Mitchell, I think she has the title of being the first professional female astronomer in the US.
Absolutely true.
She discovered a comet while she was a young person living in Nantucket, and then she turned that into being a professor of astronomy at Vassar.
Wow, you knew all the rest.
Yes.
And I believe I was told the first faculty member, not the first astronomer faculty at Vassar, but the first faculty at Vassar.
Oh, maybe. I don't know.
Which sounds pretty amazing. Okay, so that's Regina Jorgensen, another director, and another student of Art Wolf. So we've known each other for a long time. And then the majority of the folks are young mentees, Nicholas Tejos and Wenfei Funger. Some of the older folk. And a couple more. You'll see results from this gentleman who's a resident of Maui. This is sad but true, who lost his home to the fire. Now a PhD student at Stanford, working with Susan Collins, Susan something, new faculty. And Mariah Mitchell, as Dr. Lotz, can I call you Jen?
Yes.
As Jen just alluded to, runs an REU program, has for decades. To some extent, you might say they invented REUs before the NSF had any such a thing. And Regina wanted to run a post-bac program, so we started doing that with the NSF. And these are 2 of them. And there's others because of another NSF grant that we share. So if you have a post-bac, a person that might benefit from a post-bac program, be aware of this one. Okay, the talk will be on the cosmic web. It's been one of my focus. Can I turn off these?
Yes.
I'm gonna try.
It's the far ones, yep.
That one or that one? That one.
Yeah.
Thanks. Been one of my cited foci for decades, I guess. Maybe when you hear the term, you think of a graphic like this. I'll remind you, this is not data from the universe. None of your telescopes, none of my telescopes. This is from a computer simulation, and pretty much everybody's computer simulation will produce something like this. So it's a paradigm, but a difficult one to test because most of that matter is unseen or difficult to see. The galaxies are an exception. So imagine galaxies where the orange blobs are, and even clusters of galaxies where the biggest sets of blobs are. And so we do have data that supports this model, but most of the stuff unseeable. Just kind of the story. I already mentioned the galactic halos, the orange blobs, and then the stuff in between the halos we refer to as the intergalactic medium. It's well named, and acronymed IGM. And sometimes synonymous to cosmic web, but for me, cosmic web is everything. It's stuff between the galaxies, but also galaxies. On large cosmic scales. I didn't say that. These are big scales. Galaxies are, but a dot in the image. Okay, do we have evidence for this beyond the fact that galaxy surveys show galaxies line up in what we would call filaments, kind of threads of the cosmic web? We've had data supporting this paradigm for decades, although in the early days everything was a spherical cow. There was no cosmic web. And so it took time for us to convert data like these into a description like that. Here is a quasar spectrum, optical. We're going to redshift 2 quasar, a little higher. And that's the emission from hydrogen to quasar. And most of the features in here are actual signal as an absorption, not noise, even though it looks like noise to the untrained eye. We call it the Lam alpha forest. It's the lingo, which I would call the IGM as well. It's evidence for the intergalactic medium. And then this strong absorption thing, which we call a damped Lyman alpha system, is a galaxy. So in the previous slide, the galactic halos, those things are evidence that those exist in the distant universe. From data like these, we inferred decades ago that over 90% of the baryons in the universe are highly ionized and are in that cosmic web, in that intergalactic medium, with a small fraction of order 5%, few percent in the halos, in the galaxies. When you go to higher spectral resolution, higher quality solenoids, this is a spectrum from Keck, you see, again, it's all signal. The absorption is due to the threads in the cosmic web and occasional galaxies that lie between us and the quasar. So these slides were for Kathy Roth. When did she retire? Zen, did you probably know overlap with
No,
her?
it's been before my time.
Yeah.
Yeah.
Probably about 8 years ago.
Thank you. Voice.
Yeah.
Tom Jabal.
Right on. Tell her I miss her. I haven't seen her before that even. Well, when we do the same experiment, take a spectrum of a quasar at low redshift, still observed wavelengths. This is true ultraviolet wavelengths observed. So this is a space telescope spectrum, I think HST. Again, the quasar emission, hydrogen, and then not much of anything. Okay, so where'd the forest go? Puzzled some of us for a while. Where'd it go? Did all that gas go into the halos? Or was it for some reason just unseeable in data like these? And if I went to higher spectral resolution, higher solenoids, the story holds. You don't see this, you see this. All right. Complementary to that picture is something we have referred to as the cosmic missing baryons problem, which I'll now introduce to you. Some of you. And it stems from a very precise measurement of the baryon mass density. Omega baryon. And we have two experiments from the early universe that both estimate omega baryon. One is using deuterium, that's the D here. And so that blue stripe is quasar absorption line data again, similar to what I showed you. When we measure deuterium, we use the theory of Big Bang nucleosynthesis, and we make an estimate of omega baryon. I can tell you more if you want, except that. Totally separate from that, we take a space telescope, we measure the cosmic microwave background, we perform spherical harmonic decomposition, we compare that to somebody's model of how light propagates through the universe, and make another estimate of the baryon density, sorry, it's the gray, and they agree to a few percent. They agree, obviously within the errors, uncertainties, and they provide a few percent constraint on the mass density of baryons in the universe. I like to say this is a number that I would certainly bet my life on. Two completely different experiments, totally different data sets, totally different apparatus, totally different theory. Same answer. All right, so what? Well, and you probably have heard by now that we learned from this that 4% of the 4.5% of the mass energy density of the universe today is in baryons. Well, so in 1998, Fukugita did a different experiment counting up the baryons. He did what most astronomers might think to do first, which is count them in our backyard. Count up the amount of baryons in stars, so just count galaxies and how much mass is in a galaxy. Blue and the orange. Use 21 centimeter data to count up the atomic gas, that's the red. Use CO data to count up the molecular data, that's the gray. Use X-ray telescopes to count up the hot plasma in clusters, that's the black. And you can see the expectation from this is the full pi, and the Pac-Man that's missing is the missing baryons problem. So in 1998, they inferred half, if not 2/3 almost, of the baryons could not be directly counted with our telescopes. That set myself and quite a few others off on a, I won't say wild goose chase, but a chase to find that missing matter. Down the hall from Fukugita were Chen and Ostraker at Princeton. Fukugita visited IS frequently, so down the hall when he visited at least, were Chen and Ostraker, who ran computer simulations. And in the same year, well, when they heard of this conundrum, they said, oh, well, we'll look in our computer and tell you where they all are. And they invented this name for this phase of gas, of baryons, warm, hot, it should be ionized. I always get that wrong. Warm, hot, ionized medium, aka the WIM, it's kind of a cute name or acronym, where the majority of that missing material, the stuff that we cannot see easily with our telescopes, is in a hot temperature of 1,000,000 degrees, 10 million degrees, and low density regime that makes it very difficult to detect directly. So that's what they predicted. Same year, Fukugita posed the problem. And for the 20 years that followed, myself and others used every telescope at our disposal to find that WIM or that missing matter. I estimate myself alone, the programs I was on was probably $50 million of US operations, and we never found them. So a wild goose chase in that sense. We used Keck. Gemini. I think I used Gemini. We used Keck, we used Hubble, Chandra, and we used, what's that telescope? Second quiz question. This is an interactive talk. The FUSE satellite, an ultraviolet mission, which detected oxygen-6, which was indicative of that WIM, but not majority of the matter. So along came this. Let me pause there before I transition to fast reverse. Any questions on the introduction? That sets the stage. Missing baryons problem, 20 years of hunting for an ionized plasma that computer simulations say was in a 1,000,000 degree-ish gas and low density. All right, so it took a completely different approach and a completely different source to crack this problem. And fast radio bursts and a venerable telescope named this telescope. Uh-oh, no. Nobody? Parkes telescope in Australia, single dish, and serendipitous as in totally unanticipated fast radio bursts, which make them fun in and of itself. Discovered by Duncan Lorimer, so we sometimes call the first one published the Lorimer burst. And this is a beautiful image of a fast radio burst. Someone says FRB, this is what you should picture. This is the image. And what is being plotted is the arrival time of the photons of the burst as a function of their frequency. The y-axis. And you see the lower frequency photons arrive later, almost a half a second later. That sweep is predicted directly from electromagnetism. We were all taught that in one course or another, which says that the speed of light is retarded when you're in a plasma and by the frequency squared. So that's what you're seeing here, this 1 over nu squared behavior. And the magnitude of that sweep, not the shape, let's say the amplitude, is also sensitive to how much plasma you travel through. And so that DM is not dark matter, that DM is dispersion measure. You should have learned about that in an ISM course. DM, dispersion measure, and it's the path integral of all the electrons, all the plasma between you and the source. And if you go to cosmic distances, you have to include a scale factor. Right. And I like to say, and I think it's true, that when I saw this paper, we were discussing it at Santa Cruz. You were still there in 2007, but you might have just left, just a couple years. We were doing morning coffee those days on the couch, and I saw that, oh my gosh, we can count electrons to cosmic distances. That's how we can solve the missing variance problem. So the ultimate, we can count electrons. I'll mention pulsars here and there. These are like a pulsar. Pulsars also show the dispersion measure from the electrons in our galaxy. So we've known about and measured dispersion measures for decades. But not with a value of 375, unless you're pointed pretty much through the disk of the Milky Way, as you'll see now. This is a map of the dispersion measure on the full sky of our galaxy. It's from a model. It's a well-determined model from data, mainly from pulsars. It's called ND 2001. It's one of the most highly cited unpublished papers on arXiv. And if you're in the plane, you can have hundreds of DM. It's got these funny units, parsecs per cubic centimeter. You can have hundreds, even thousands in the plane. But once you're off the plane, you're down into 10, 20, 30 DM units. It's the Milky Way. And Duncan's source was in this direction on the sky, towards the Magellanic. Oh, I should have made that a quiz. That's where the Magellanic Clouds are. Galactic coordinates. He was looking for pulsars in the Magellanic Clouds. He made a mistake, and in the software that he wrote to search for this signal, this sweep, he allowed the dispersion measure to go much higher than you would ever think of doing for the Magellanic Clouds. Something like 50 would be maybe what you'd expect for the Magellanic Clouds, not 375. So it was serendipitous in the sense he wasn't looking for it, and he also had messed up his software. And it took him 5-6 years after he had taken the data to mess up his software. So it was sitting on the hard drive for 6 years. And then they found it. Again, it's much, much higher than what the Milky Way will give you, as well as anything reasonable for the Magellanic Clouds. So they asserted in the paper, and they were correct, that it lay at cosmic distances. And that beget the field of fast radio bursts. Okay, so back slowly towards the missing variance problem. I've hopefully convinced you DM is the dispersion measure encodes in it the path integral of the electrons. So that's an awesome electron counting machine. And we can predict from effectively first principles, let's call it that, the average cosmic dispersion measure. That's what I'm showing. Average dispersion measure from the cosmic web. And it's just that path integral I showed you. Integral NE over 1 plus ZDS, where now DS became the gobbledygook of cosmology. NE is still there. And NE's depends on how ionized the helium is. It depends on how many baryons there are in the universe, the missing baryons problem. And what fraction of the gas is highly ionized, diffuse, D for diffuse, which is 85% of it today and 90% more than that at redshift 1. So most of it's ionized. Right. So this is a plot of that quantity, redshift, and the DM cosmic derived for the Planck numbers. 15. And it roughly scales like 1,000 times redshift. So we have a target. If we have a means of measuring the dispersion measure of the cosmic web, and if we have the redshift of the source, then we can test whether the baryons are actually there. Now, a few words on DM cosmic, and it'll look like I'm shoving things under the rug. I am for the presentation, not for the calculation, not for the analysis. Anywho, dispersion measure, there it is, equation. I like to call them a blessed, or that quantity, a blessing and a curse. It's a blessing because it does allow us to count all the electrons in the universe. It's a curse because it also counts all the electrons in the universe. And if I'm interested in the missing baryons problem, the cosmic, then I only care about this portion of the dispersion measure. I don't care about the electrons in the Milky Way, or the local group, or the Milky Way's halo. And I definitely don't care about the electrons close to the source. I will start calling the host of the FRB. And I don't really, I have no way of tagging, I get one number, this is a scalar. I have no way of separating those out. I have to deal with them all together. So we do. I said that. The Milky Way, we have a very good model, have had one for decades, again, informed by pulsars. So I'm not worried about that number, that contribution. The Milky Way halo is still an open question. In fact, FRBs are placing new and important constraints on it, which I can talk about afterwards. But that's an unknown number of order of 50 units. So that's got to be part of the model. And the host is, I don't know, it's a nuisance. It's a great nuisance for this analysis. We expect it to be something like the Milky Way. So again, something in the order of 50 units, but I don't know. We don't today really know what FRBs are. Makes them so kind of fun. But that means we don't know where they, well, we have data that gives us an indication where they occur within galaxies, but we don't know, we know rather little on the very fine scale, say parsec scales of the source. All right. That said, oh, right. I'll come back to DM cosmic, but that's kind of the full laundry. Need this part of the equation too, or part of the graph, the redshift. The first order 10 FRBs detected were with that Parkes telescope, that single dish. And its localization uncertainty is arc minutes. This is a circle of 5 arc minutes, I don't know, 15 arc minutes, I forget, something like that, 10, let's say 10 arc minutes. And I think most of you appreciate within that circle are gazillion galaxies. And I cannot tell you which one's the host. And there's nothing else in the signal other than that dispersion measure that not a bit strong, but there's almost nothing else in the signal that's redshift. It gives us an indication of redshift. So our approach is to identify the galaxy that occurred within. This is like gravitational waves. Sure. More familiar with that, and then get the redshift. It's also a bit like some of the supernovae, some of the gamma ray bursts. This was the game changer, this telescope, which I won't quiz you on because it's written up here. The ASCAP telescope, one of the pathfinders for the SKA. And Keith Bannister leads a team called CRAFT, which is largely a software computer experiment to detect FRBs on ASCAP. I learned over the years now, I'm not a radio astronomer, never will be, that all the effort is in the computing and software. I mean, you got to build the dishes. It's not like some special antenna or some special instrument. It's sifting through the data as efficiently as you can to find these FRBs. And by data, I mean the data rate of ASCAP is 1/10 of all the internet traffic. Like Ruben's like, oh, we had a big problem. Yeah, 1/10 of all the internet traffic. So you don't save the data. You cannot save the data. You analyze it in real time with as much compute as you can afford. And cool, this is where I learned they calibrate software in watts. How many watts is your algorithm? Because cooling becomes the limiting factor. Pretty cool. Anywho, they turned that on, and in 2018 detected and localized at the same time an FRB. I don't know if I have the name here. I know its name, 2018-0924b. That took them probably a week to get the data from the telescope to a computer. And then they saved 3 whole seconds and then analyze it and double check and triple check and blah, blah, blah. Anywho, the moment they had a localization that they were confident in, I took a spectrum at Keck and then we followed it up to Gemini South. You all were part of the story. Of this galaxy, the red, you can't maybe even see it, there's a red dot there, that's the localization. The association is probabilistic, it always has to be. There's no, again, there's nothing in the signal itself that says it's this redshift. We associate it by its position on the sky and have a formalism for doing that now. And there, bang, redshift. Pretty easy once you have the spectrum. That was 2018. By the middle of 2019, we had about 5 or 6 and decided to write up this paper. Jump the gun. Black curve you've seen before, that's a straight prediction from cosmology. The gray is an estimate of the physical scatter, which I'll speak on more as I head towards the end of the talk. That's a model, the gray. And we're now setting out to constrain that model. But let's call it a guess. And you expect a physical scatter because the universe does have structure. So you don't always get the average value, you get some number around the average. For the plot I'm making, but not the analysis, I'm going to plot the data, DM cosmic, given the value we measure directly from the data, very precisely, minus the Milky Way estimate, which I talked to you about, and then some guess for those. We took 50, because that was similar to the Milky Way, and like beads on a string, the quality, the ones that passed our quality checks, the ones in color, landed pretty much right where they belong. And we asserted that, published that we detected the missing baryons, and Fukugita himself agreed, so that was good. We now call this relation between redshift and dispersion measure the McCord relation, named after J.P. McCord, who led the paper and then passed away unexpectedly a week later. So it's in posthumous, named after them. Any questions here? I'm gonna now attack the gray region next. Finish up.
Those ones that are way off the relation, are those just serendipitous? I mean, just ones that don't happen to have either have a lot more than.
So I
in front of
remember
them?
one of them, as I said, we had strict selection criteria, kind of like if you're familiar with supernovae, the gold sample of cosmological supernovae. We have similar such criteria for the FRBs. I remember one of them had extremely high RM indicating a large local contribution, and I forget the other one. Let's see, I can remember by name. Oh, the other one, there were 2 galaxies, and so it was ambiguous. They were at the same redshift, but the contribution from each was too ambiguous for us to include. And a third, the circle on the upper right, I don't know if you've seen that one. That one had also a not so high probability association to a galaxy. So we did not include that one either. Despite it lying close to the line. Okay. Sorry, any other questions?
Yes.
Yes.
So So in this plot, the little bit higher redshift FRBs are kind of in a good agreement with the theoretical line. Is it because the distant ones are more representative of average the cosmic picture?
At 5 data points, I wouldn't want to say anything, so I won't. I'll just call it one.
Yeah.
Oh, I think it is.
And then the second question is it kind of like routine that once you see the FRB, is it relatively easy to
Right.
make identification?
Yes, it turns out. I don't have, so the student that's been leading up most of the FRB host galaxy work is in YMA today. She has shown that the luminosity of the galaxy is around half L star, which if you know your galaxies, half L star at these redshifts is duck soup. It's easy. Even public imaging typically shows the host. Gets harder out here. Yeah. But ASCAP, its sensitivity is predicted to only detect out to about here. We were surprised to find one at redshift 1. I'll show you that briefly. It's towards the end of the talk. Good questions. Other questions? Okay, so the dispersion. So where, what next? For me, I decided to become an oceanographer. For the rest of the team, let's make some more science out of this. And the key point is this first word, locating. So we detected them, but we still haven't established if the baryons are, where in the universe, to what extent this model of the cosmic web is accurate. Call it that. And the approach that we're now taking in a couple of ways, I'll only describe one today, mainly, is using that physical scatter in the dispersion measure. And I said it in words, here's now in by graphics. Clearly, if my sight line through the universe is the red line shown here, and I go through some serious structure along the way, I get higher than average DM cosmic. Whereas if I intentionally draw a line to miss all the structure, I get a lower value than average. And that's why you have a physical expectation for scatter about the mean. But it gets better than that. We will be setting in what will be some of the strongest constraints on the heart of galaxy formation, what we call feedback, which is a word that catches many unknowns of galaxy formation. We have strong evidence for that galaxies do shove gas around. This is some data from the Deep 2 experiment. Shown on the upper left is emission of O2 from galaxies. It's about 1,000 galaxies, I think, at redshift 1. And then he plotted the magnesium-2 absorption features in those galaxies and demonstrated that they're blue shifted. The left of the redshift of the emission, and inferred that the gas must be flowing towards us. It has to. When we call that, sometimes call that an outflow form of this kind of feedback, moving matter around in galaxies, around galaxies. People do that, of course, you're probably aware, in computer simulations. They dial up knobs to make galaxies explode, or to turn on an AGN that does something like that, or to have supernovae heat up gas, or have somehow heat up the halo. They do it in quite a few different ways, and they're allowed to, because they are playing God on the computer, but also because we don't have a lot of data to constrain what's going on. This data, is not more than suggested. It shows gas is moving away from the galaxy, but not how much gas, not at what distance from the galaxy, not with a bit with what speed, but not some of their key ingredients you'd need to know to be able to nail down models like this. On the right is a plot of how much galaxies of different masses, halo masses, retain what fraction of the baryons they retain for different feedback scenarios in the suite of Simba simulations. Okay, so what? Well, we can constrain some of this, and we do it from the cosmic, the M cosmic again, but no longer the average, but the scatter about the average. And I'll show the equation that we've adopted that's informed by simulations and need not be correct, but is a pretty good description, at least today. What we're after is the dispersion in the DM. That's what we're going to measure. We'll encode it as F, this one number for now. Although the full description we give for the variance about the mean is that. So delta is the value we measure relative to the mean, and then P of delta is the PDF we use, and sigma is part of that. Oh. F is what we're after, or that's what you'll see today. That's what we've published. We, in the original paper, did not ignore the host, or just only took that 50 number in our analysis. We included both components together. If you put them together, you can call that the extragalactic DM component. So everything outside the Milky Way local group. And what we do is build a forward model of that measurable, that observable. So DM extragalactics are observable. It's what we really measure minus the Milky Way. And then redshifts, I've described how we get redshifts. The red dots are 16 FRBs only from ASCAP for this plot. And the forward model has to include a whole bunch of things. The fact that the telescope has a finite aperture. So when you allow for that, you have to deal with FRB energetics. Some of these things are the Hubble's constant matters. It's in the DM cosmic equation. This is a means of constraining H naught as well, in principle and in practice too. But for this talk, I'm after F. So we build a forward model, and you're seeing the best fit forward model to the data. The color is the PDF of the model, where brighter colors, more likely to have FRBs, darker ones less, and some contrast PDF. And that's the redshift one FRB I mentioned as well. It's not on the other slide. So that's 16. F, just a little more intuition on F. If F is big, let's go that way. If F is small, then there's very little scatter about the mean. And that's the model we would generate. If F is big, then there's a lot of scatter about the mean. So you can see from the dots, we have some constraining power on F. And Jay led that study as an undergraduate. And this is the main result of his work. H naught does matter, and no big secret, H naught is back in the news for being unknown. So take your favorite. If you like high H naught, that's the dash curve. If you like low H naught, that's that curve. If you say nobody knows what they're talking about, that's that curve. That's not true. Oh yeah, is that true? I think that's true. I forget what that curve is. Seems like that the uniform should be good. Nobody knows what they're talking about. No, its uniform's probably within those bounds. That's right. So yeah, if we say we really don't have no idea what we're talking about, then anything goes. That's the data. Anywho, you can see, maybe you can't quite tell. We get a lower limit on F today from 16 F. This tail, this becomes nonsensical in some ways. Anyways, it's a lower limit. And it's already has some constraining power. Ignore that line. Here is an unpublished work in progress by a grad student at Yale, I think. And she's plotted. Oh, I forgot to put F here. That's F. Sorry. And that's J's lower limit, 0.23 or something, 0.2, I think. And these are predictions for F from various galaxy formation models. And they're in this plot, they're varying some way that they have AGN feedback on the galaxies. And so symbol, at least for some of the AGN, are starting to fall away. And that's 16 FRBs. Not bad to start. And I'm going to head towards the finish line now. Questions on this result? So with it, I didn't say it, I kind of alluded to, I didn't say so much in words. Again, low F, better than this one. Low F means there's very little scatter about the mean. What that means physically is that all the baryons have been distributed throughout the universe. You almost have a homogeneous universe. So a lot of feedback. Big F it's counterintuitive. Big F, all the baryons are in the halos. They haven't been ejected. And that's what we're pushing on these days. Okay, so we're not done by any means. So FRBs are also fun because the field's still on the exponential growth side of things, despite that blue curve. Yeah, still on exponential growth. The blue is total FRBs published. Is that true? You want to say that? No, not even published. Total FRBs from the CHIME experiment in Canada. They published 500, which is kind of here. And then the black curve is the growth rate of localized FRBs, ones where we are precise enough that we can get a redshift most of the time. ASCAP I talked a lot about today. Another experiment just turned on, DSA, that's in Owens Valley. ASCAP's upgrading, so that curve's about to go up. CHIME is upgrading so that these are all unlocalized or big enough errors on the localization that you don't know the galaxy, but that's changing for CHIME too. That's what that slide says. So they're putting in, I guess I'm part of the project now. We are putting in outriggers in Canada, at Green Bank, and in California, at Creek. I think that's the one in Canada. That one's operational. And we have yet to use Gemini. We're about to be using Gemini to get the red shifts of some of these. That's the next slide. So thanks to the tech, we have a large program approved. Tarane Eftekari is Tarane Eftekari is our PI. Her program starts in 2 months. And we awarded 200 hours between the two, north and south, using GMOS on each telescope to get redshifts. My goal is to get 1,000 FRB redshifts. We have 16. Well, we have 16 published in that paper, about 50 today in the community. And Gemini will play a big role in getting us towards 1,000. With that, what is today a lower limit that I showed you on F, this is just a forecast with 100 FRBs that we'll get here next year. That starts to get even more constraining on galaxy formation. The other approach to leveraging the DM and galaxy formation is just to cross correlate the signal, the DM measurement with foreground structure. We do that with a project called FlimFlam, led by KG Lee and Sunil Simha and Ilya Kirkin, to resolve the cosmic web. See their papers for more. That's a forecast of what we can do. I think it's 100 FRBs with FlimFlam on constraining how much of the baryons are in the diffuse intergalactic medium, the nuisance parameter, and how much the baryons are in galactic halos. It's a forecast. That's not a result. We get lucky and a sightline goes next to an individual galaxy of interest. You can study that in ways that are quite complementary to quasar absorption lines. Constraints on magnetic fields, there's a rotation measure in every one of those FRBs, which is sensitive to the magnetic field. There's a scattering of the signal, which is sensitive to the density and fluctuations, turbulence within the gas. Some of these have occurred in clusters already. 2 of them have occurred in A-bell clusters. 2 of the localized ones, not of the 5,000, 2 of the 50. And Liam Connor published a nice paper asserting that quite a bit of the signal in the dispersion measures from the intercluster medium. So an independent way of probing that diffuse gas or that ionized gas. I have a student named Lordrick who's working on M31. So this is a model, a prediction, called that model of M31's dispersion measure. It has a halo, we think, should. And this is the red dots are 4,000 FRBs from CHIME. We can perform a differential experiment to infer M31's halo. And you had asked about the host, how often do we see a host? Almost always. I know 2 out of about 40. One which we keep trying with HST, JDOST, Muse, and no tackle give us more time. I guess it's not worth, it's only one galaxy, what are you gonna do? We're trying. Magnetic field, I talked about that. Our own halo, I mentioned that. That's it. So where the field's at today, I'm pretty confident all this stuff will happen. I've talked about a number of those things. It'll probably become useful in H0 for Hubble constant. It's a completely separate technique from everything else, so its own systematic, its own challenges. Lensing, I think, will become very exciting. I don't even know that much about it. I can tell you it will. And then I don't know. You see papers about FRBs doing everything. I think everything gets a bit too much. Thank you.
You guys have any questions? Are there transient optical counts to these?
Sorry, I should have added a slide for Gemini. That's embarrassing.
And then that would help you figure out the right,
Yeah.
which is the right thing to get them.
It's not my computer, which was what I asked for. I'm gonna try. Brian, I hope I don't break anything. If you're listening. You also be familiar with that name, Alapetke. Kilpatrick Tejas. That should be enough. There we are.
Yeah.
Sorry, Jen, I should have included a slide on this. It's my bad. So yes, one of the FRB. So I didn't even say the word repeating until now, which is kind of funny because it's important to fast radio bursts of order 10 to 20%, say 10% have been demonstrated to repeat for sure. The first one that was localized, that's why I didn't say that. I skipped those slides. Repeats. One of them has a quasi-regular chirping, 16 days. Funny number, but regular enough that the tech for Gemini North lets us stare at that part of the sky. Over that part of the sky. Oh, try the power. Yeah. There's a galaxy with a known, we know the galaxy's hope. Lets us stare at this patch of the sky for 30 minutes. Not every 16 days, because Alapetke is not available every 16 days, but whatever. Frequently. The same time that Chine can see that patch of the sky. So we coordinate looking for an optical signature at the same time that we'll detect radio. And we've had 2 successful campaigns in the sense that we observed when FRB occurred. This is a bit busy, but those are counts from Alapetke. It has 2 cameras or 2 detectors. Does it have 2 cameras? And the dashed lines where the FRB occurred, you know that very precisely. And you don't by eyeball see anything. There's nothing. This is a zoom in. So we've made the measurement, but not detected any photons above the noise at this stage. And but it's still it's very valuable. Yeah, I'm embarrassed to include this. Yeah, it's not the easiest plot to digest. I'm sorry. It's a good plot, just it's a bit for the experts. That's the FRB energy on the x-axis. Not all repeats are the same in terms of energy. And we didn't get a particularly bright one yet, despite what this looks like. Oh, because the orange are pulsars, they're not fast radio bursts. And then that's the optical to radio, so optical Gemini radio from Chine. And placing some constraints on one of the 50 or a handful of the 50 models that are in existence. So we have an approved program still to do this without Alapetke. And yeah, this is the name of the FRB that often chirps every 16 days. That game is going to open up as well. There will be many more really close by FRBs detected in the next year or 2. And I think I forget the southern counterpart.
Sorry.
Thank you.
They both mean fox.
Yeah.
One in white, one in Spanish.
Oh, that's cool. They're both going to play a role. That's the biggest fast readout camera on a big telescope today.
Any other questions, even on Zoom?
This is Tom again. I'm way out of this field. I have a kind of silly historical question, but I remember hearing or reading in the early days of these that some of these fast radio bursts were ascribed to people opening microwave ovens.
Oh,
in the
yeah.
observatory. Is there any truth to that?
Very much so. And then that signal, yeah, it's still a signal. There's no quotes. That signal became known as perytons, Pryton. I don't know where that came from. I don't think it means fox in Aboriginal Australian. But yes, so between that first event that was published in 2007, I said there was about 10 from Parkes. In addition to the 10 legit, there were about 5 signals detected at Parkes that look like FRBs, so that's sweep.
Did they have velocity? Did they have dispersion?
Not quite, and I don't even think it was. I can't remember. It must have been something like a new squared, otherwise they would never even been in play. But I forget that I forget how they're different. Anyhow, Emily Petrov especially is credited with recognizing those events were occurring at lunchtime at the Parkes and identify they were microwave events, as in someone making their lunch microwave. Yeah, so that cast some additional doubt on the field, which is kind of fun, because this was still before any had been localized, so that there was no smoking gun to the extent that we have one, that they're extragalactic. Yeah, that's part of the fun story too. Perytons.
So when you take like optical spectra, you get the kind of rich information other than the redshift, and they help to kind of narrow down the error bars for the intrinsic dispersion measures of the galaxy.
Great question. So, question being asked. So I've emphasized a couple times DM host is a nuisance to our analysis. So how much of that signal is from the host galaxy? We do have nice data on the host galaxies from Gemini and other telescopes, and a spectrum. And in some cases, quite a precise localization, so that we've shown without beyond a shadow of doubt, they're not all occurring in the center of the galaxy. So one of the 50 models was FRBs are all from AGN. That model died early on. Alex Manning's, who went by too quickly, her last chapter of her thesis is looking for any correlation between a host galaxy property and dispersion measure, or anything in the FRB signal. As of today, there's nothing published. I think I can even say there's nothing published other than this. Actually, this is her work. She's a student at Santa Cruz. And here she's estimated the dispersion measure from the host. I'd have to tell you how I could, but just accept it for the moment. And then the rotation measure that's dominated by the host. That's expected. And that's, there's a correlation there, but not a very good strong one. And that's about the only thing we've seen so far. But yes, in principle, I fully expect, as a scientist at least, the events that occur towards the center of a galaxy should show a different dispersion measure on average than far away. And the more massive galaxies should show a different dispersion measure than them. But as of today, I don't know, let's sample about 30. Nothing that's left out.
And so probably orientation.
Orientation could matter, yeah. Yeah, I agree with all that. But nothing has popped out yet. Yeah. Yeah, oh, right, that's another Gemini hook. Alex is, there she is. They just put out, she's second author, the first was one of those post-bac students. They put out an archive, Gemini AO observations of 5-ish of the galaxies, partly to get the inclination and morphology of the galaxy at high precision. Yeah. And that work continues. I don't think the tech gave us more time. That work continues on Kepler and HST.
Any more questions? Oh, now we can thank Thanks
My
again.
pleasure. Thanks for having me.
We're gonna have lunch outside if anybody wants to join. And Ella and I.